interesting. This is using music, generative by playing music. It's kind of fun. So maybe we play this one.
Yeah, so those figures look interesting.
Hmm?
Hey, did you see?
Floor plans?
Did you see a little cup?
It's already generating a huge interest. I'm scaring everybody off.
Little round.
Oh yeah.
Oh,
Oh, here
of
it
course.
is. No, but-
No, because, you know, we have these all huge debates in architecture ever since we started working with computers. What is creative and what is the authorship? And now it's going to change again, because based on this you can create smaller tools. They will understand geometry. And if you have constraints of geometry and trained set, you can start from somewhere. And then you can put, so what is our skill exactly? You know, that's a big question for architects. We still talk about representation, not understanding that we gave up idea of a model and use representation as a story about it. But anyway, there's a, yeah. So when you go into into how weird we are as a discipline, it goes to some crazy.
Architects.
Oh my God. Artists are even worse, so both of us are like, but these are really encouraging because we only have 64 tiny little, it's a tiny start.
Yeah.
Compared to what we actually have 10,000.
We have 10,000 pictures.
9,876 because we went down, sorry.
Yeah, I think it's interesting.
It should be fun.
I'll be interested to see what's happening with it. All right, so just to recap a little bit. Basically, what we talked about on Monday is like how representational learning in that sense works from like basically raw input signals, which are in this case the pixels, like that each layer now tries to learn a more and more abstract version of the input, so that at the end we have a representation that makes it fairly easy to conduct a certain task that would be present within the data. We talked about how we can learn this part of the stack in an unsupervised fashion, and for that purpose we talked about autoencoders, and where we have, for example, like very large amounts of data, but without labels, and we can go from basically the input over a bottleneck to back to reconstructing the input again. So like that's the way how we would try to turn this unsupervised learning problem again into a supervised learning problem. So where we try to reconstruct what is present. And since we also talked about like how we would run into trouble if we just try to use the basic models and the basic neural transfer functions and the basic backpropagation in these very deep architectures. We talked about how we can train or learn this autoencoder with many layers in a stacked or iterative fashion, where we basically just first train the first layer, then remove that output part, add a new layer, and try to reconstruct it again. And in this case, you can either, again, go from the input to the full output, or basically also just think about fixing this part and basically using these outputs as the input, putting it through a bottleneck and try to reconstruct those labels here, or those outputs here. So that's actually kind of where you can stick to a very small iterative version to that. All right, so we talked about how we need to force our information that we have at the input through this bottleneck, so that we don't learn just some simple or some trivial basic representations. and so that we actually learn something that is important for our task, for our information that's present in the data set. And for that, we said, okay, we need to have a bottleneck, and one way to have a bottleneck is to reduce the number of neurons significantly in these hidden layers. But another way to enforce this is to just have layers in there that are forced to not be very active at all throughout the training and the testing phases of the neural networks, or like the autoencoder in this case. And we introduced this as through the a desired average activation of each of those hidden neurons over the entire test set, or in most of the cases when you train these models, you would use like mini batches, so you would have basically a mean activation over a mini batch, which is typically like 30, 50 kind of inputs at a time. That just makes it a bit easier, a bit faster to train. As you can imagine, that through the use of these mini batches, you can start to parallelize your network pretty easily as well through like GPUs and so on. Okay. So we would compute the average activation of each of these hidden neurons, and then identify if they are within a certain threshold or within a certain desired amount. And in this case, we would, for example, desire them to be active only like 5% of the time, or their average output should only be like 0.05 overall. And you can already imagine that this, to achieve these kind of characteristics, it's a lot easier if you just use rectified linear units, which have a lot of zeros in there already, and then you have the direct output x after a certain threshold. In most of the cases it's 0, and you should not, or you often don't use those other traditional activation functions like tangent hyperbolicus, which for example has a minus in there, so it's from -1 to 1, and so on. So that's kind of like one more reason why we use different types of activation units in these networks. And then to measure or to punish these neurons that are activated more than we would have them desired to be activated, we can compute something called the Kalbach-Leibler divergence, which basically punishes if these two values are very different from each other. And a nice property of the KL divergence is that, and still within these deep neural networks, we still have to do gradient descent. So a nice characteristic of this is that if you take the first derivative of this function, all these logs fall away, and it gets a lot simpler to compute, and it's not very complicated in that sense. And for your reference, I have this plot again. So in this case, we have like a row value of 0.2, and if the other, if the row hat for each neuron, for example, will be 1 or 0, there you have an additional penalty that is produced for each of these neurons. And to impose this kind of regularization onto the model, you now just use the same error that you had before, which is the reconstruction error. So in autoencoders, you want to reconstruct the input in the output, and you add this additional term to it, and basically now you have this entire loss function or error function that needs to be derived for each weight separately, and for each layer, and then you have the backpropagation as in the simple multi-layer perceptrons as well. So this is how our update function now looks like, and you can see that the KL divergence now looks a lot simpler through the first derivative. And we also introduced this beta parameter, which in this case is like the regularization weight that allows you to weigh both the reconstruction error with the sparsity error with each other, and so you can try to increase this part through increasing the beta. However, if you increase that too much, what will happen? Well, the neural network will be forced to not produce any outputs. So if you have, like, I don't know, it depends on the size of the input, but if you crank that up too high, like 10,000, 20,000, and you multiply this with your KL divergence, well, then that error weighs a lot more. So what you have, what will happen is that the neural network will go silent most of the time, so it will not produce a lot of outputs. But if you make it too small, well, then it will learn this this direct or trivial representation. And this is a little bit of a caveat here, because obviously, if you want to measure your performance by being able to reconstruct the input at the output, and you, for example, have like an image that you have as input here, and as output you want to like look at that image again, and it looks very, very similar, it looks very good in the reconstruction. Well, it could also mean that you actually had this value too small, and these representations are basically trivial, just pushing the information from the input to the output through without learning any kind of learning any interesting representations. And so this is sometimes a little bit of a problem if you think about only unsupervised learning, where you don't really have a statistical evaluation except for like visualizing the loss function for evaluation purposes. But for example, like even if you do these unsupervised tasks or learn these unsupervised autoencoders for representations, there should be somewhat of a target application at the end that has maybe some labeled data sets or data points for which you want to like perform well in the classification. So it's kind of like a surrogate task that you want to evaluate your representations on. So it's just kind of like try to be careful with like manipulating this term here, and yeah. So it's often a bit more complicated than just like trying to find the optimal hyperparameter, because obviously we would have to validate not just for the reconstruction loss, maybe for reconstruction loss and the KL divergence and the like a surrogate task, like a classification performance on a smaller data set that's like subsequently tested on. Okay? Alright. So then we talked a little bit about representational learning for human behavior. I brought you this example of the vowel space, where we were interested in kind of like representing the like size of or the frequency variation of an individual of the 3 cardinal vowels, where the tongue is at the most extreme positions, and we visualize that in this graph here, where we have all the dots that are learned or that are observed, the representation that's present for the entire population of English speakers, and then for each individual the green kind of triangle, which basically represents the location or the relative size of this individual's vowel space with respect to the entire population. And we found, or we saw, that we can observe that individuals that do not suffer from depression have significantly higher or like greater overlap with the reference population, while individuals with depression have a lower overlap. And we saw that in a large data set. We just got confirmation that we are doing this challenge again this year for the ACM Multimedia Conference. So if anybody's interested in participating in this, we're gonna have this happen in October, I think. October or November, and the ACM Multimedia Conference is going to be in San Jose, I think, this year, so it's not that far. Okay, so yeah, we saw that we have significant differences in the behavior of these individuals, and we try to achieve one type of goal in this context, and this basically we wanted to quantify what previously was qualitative observation in actual quantified manners, and so this is kind of like what this slide is also about, basically, where we take a human's behavior and then kind of compare that to reference populations and try to like give this as an additional objective tool to doctors to assess a person's well-being. Okay. And then we talked about speech and motion recognition. I gave you this example where we actually did train deep autoencoders in order to learn representations naively with unsupervised, no additional information on like what the audio samples represent. And we found the following things: that first of all, it was possible to kind of split out this yellow class, which we colored at a later stage. So we gave the data to the autoencoder in an unsupervised fashion, and then only later colored each dot corresponding to the affect label that it had in the data set. And we saw that also like on the kind of like extreme opposite side of this spectrum, so to say, we observe these green dots, which are the angry dots. So we have sad dots and angry dots on extreme sides of the spectrum. We can already kind of guess that while there is no change in the affect dimension of valence, so both of those emotions are negative. However, there's quite the difference between them in the sense of intensity or arousal or activation. And we can actually visualize that better in this pleasant unpleasant, where blue is unpleasant, so you have kind of deep blue down here and deep blue up here, while you have deep red right next to it, and kind of like the gradient of red all throughout, so that you don't really have a good separation of positive and negative affect. However, you get a much better separation in arousal or activation, where you have high arousal and deep red colors up here and deep blue colors down here with low arousal. So what we learned through this kind of like is that if you completely learn these unsupervised models without any guidance from outside or from what you believe is in the data, then the neural network will jump onto like what is most salient, what is most important to reduce its reconstruction error, to reduce its general loss, and basically you will end up with something like this, which does not necessarily correspond to what you might want to do with that. So there might be something about, like, maybe for example, one way to remove this like intensity gradient would be to normalize all your data, right? So if you remove all the intensity variables through, I don't know, a normalization, a z-score of all the wave signals or whatever, then you might be able to remove this. But obviously that involves a couple of other issues where you have to look at all the data, you have to pre-process it. So it's not as nice as just sending in the data and seeing that like it learned something interesting. We also then evaluated this because we didn't just want to see reconstruction error, and so our classification task in that sense for emotion labels was our surrogate task in this context, where we tried to use these representations to learn useful or meaningful emotion separation, and it works for some and it doesn't work for others. And after this paper, we actually published a couple of more papers, and I think I'm going to talk about one when we do generative adversarial networks, and where we improve on this performance quite a bit and try to actually get better at the valence separation and not as strongly separate the arousal dimension anymore. Okay? Other questions? Okay. So we can now briefly talk about the word embeddings before you guys are going to do your presentations. And so word embeddings is quite interesting in and of itself, and I brought some examples actually. And so what is actually happening here is that language is quite interesting, and there are relationships among words, and we want to often kind of like learn to better represent what's going on with maybe less of a language type of data input. So what is the first problem? Well, the first problem is all of our neural networks really don't like symbols, right? They like data. They like continuous real numbers that is quite different from symbols, right? So one of the things is so if you have like the word, I don't know, like we have in this case the word train and track. Well, in a symbolic world, the two words are not the same. That means they're not equal, so the distance is 1. But train and train are the same word, and so the distance is 0. Even though they could be also two different words, right? You can have a train that runs on tracks, and you could have the verb to train, right? And so the symbolic world is a bit problematic because of these kind of things. So you can't really do like nice distance metrics like Euclidean distance or something else. So that's a little bit of an issue. So what we ideally want is to have these words that are symbols now transported into a world that is numbers and is easier to deal with. One way to do that is a bag of words, right? So you just have in a long dimensional vector always like every single column represents or corresponds to a word, and you would set the word, the column to 1 if that is the word that you want to represent in this one bag of words. And you can add more words to that bag, and then you have like not just only one in there, but like a bunch of ones. Maybe you want to normalize the bag of words with the number of words that you have, and you get something that Luke spits out, which is a software that basically does word count and normalizes with the length of the text. So you can see that there are multiple ways to kind of now bring these symbols into like a real number world, okay? However, one of the issues with bag of words is if you have a vocabulary size of like 1 million, right? And you want to bag of words, I don't know, like maybe a sentence, right? This vector is super sparse. Like you might have 10 ones in there that are present, and everything else is zeros. Okay, so that's not ideal, and we don't really like that too much when we deal with data and with machine learning. So what we want to do is actually kind of take this bag of words vector and transport it into, instead of a sparse world, which only has a few ones on, into a very dense world, where you have small number of dimensions, maybe like 100, 200, maybe more. But each word now lives in this world of like 100 dimensions, and you can do all the other stuff that you have access to, like you can compute similarities with words, you can move from one word to the other, you can basically find synonyms. You want to find, like you have a word like train, you want to find synonyms. Where would you look for it? Well, not on the opposite side of that world. but on the same kind of cluster when you would like look at its neighbors and try to find some correspondences and so on. So that would be what we want to have. Okay, that's kind of like what we ideally want to have, and so vector representations of words would kind of be our solution to this problem. So, and ideally we would like to learn vector representations of words that allow us to that semantically similar words are mapped to nearby locations in the vector space. So train and track will be kind of similar to each other, or train and bullet train and steam train and stuff like that. That should all be like kind of in the same location, and that works better with German because like we always have one word. Everything. Donau-Dampfschifffahrtsgesellschaftskapitänskajütenschlüssel.
Seriously, that's
one word. Yeah.
Oh wow. Well,
Uh,
practical. That is the way around it, right?
You can come up with any word in German. That's the beauty of it. So yeah, so this is kind of like something that we want to have, and how would you get this, and like how do we kind of learn something that is ideally like corresponding to these like desiderata, so to say. And one of the main ideas or the main things that lead to something like this is basically our acceptance, or like the hypothesis that we have that drives this learning of these vector spaces for words, which is called the distributional hypothesis. And that distributional hypothesis doesn't mean anything but the following. Words that appear in similar contexts, like if I say Vienna is the capital of Austria and Paris is the capital of France, right? So that's like, that could be two totally different sentences on Wikipedia, two different pages, but the structure is very similar. So through the distributional hypothesis, we can hypothesize that learning through many examples that there is a relationship that is capital between Vienna and Austria and Paris and France, right? So these words happen to be in similar contexts. In addition to that, if you talk about the European Union, you happen to like see lots of times these country names like Austria, France, the UK, Germany, and so on. So there might be a relationship between those two, right? And so you expect that if those words happen to be observed in similar contexts all the time, well, they get to be similar. So that's kind of like what our loss will be. Like we try to reduce the distance between words that we believe are similar through a lot of examples, and we will increase the distance between words which we believe are different from each other because they always appear in different contexts. So you would never talk about country names if you talk about dentistry or something like that, right? So even though that might happen. But.
Is that parsing or parse phase?
That's a different one.
It's based on grammar, right?
Mm.
So these are not grammar.
So this is all semantics.
Okay, I get it.
So this completely ignores grammar
The
structure.
Grammar.
And then parsing parse phase mostly does parts of speech, tags, and it mostly looks at syntax. So semantics and syntax, in that sense, kind of look different from each other. If you want to do, and I always feel like you want to look at both at the same time. So if you want to, for example, investigate the topic that a person's talking about and the way that they're talking about it. So what's the depth, or like what's the complexity of the syntactic structure and so on. So you can compare those. And I mean, I think that it's different, but parse phase also uses some semantic information, I think. So they first transform like the words also in a semantic
into some
space.
sort of, they kind of change the way they from Chomsky's grammars into these
Yeah, but-
relational,
But
right?
to predict the parts of speech for each
Uh-huh.
word that comes as input, they don't just use the grammatical structure, but they also use like word embeddings to predict it. So they use something similar, so they use semantic information to better predict the parts of speech. So that's kind of like the way I think, but it's mostly grammatical. But I haven't like, looked into it too much, but yes, I think
Anyways, thank you. It seems very, very interesting
yeah.
as the next frontier of going deeper
Yep.
to the text.
We looked at parsing and wanted to like change it a little bit and like build upon it, and it was like not that clear how to like open it up and like now insert our code. So it's a bit of a black box. Anyhow, so and Word2Vec, some of you might have heard that, is one of these methods that relies on the distributional hypothesis. What we want to do basically is we want to learn this embedding matrix or embedding function W that transforms a word, a symbol, and like how you would basically in TensorFlow or in other machine learning toolboxes, you would before you run this or you train this, you would first transfer every single word into a number, right? Like you never work on words. Like you just make a vocabulary or like a list, a dictionary in Python, and then you just look up like which number that word has in the dictionary, and then that's like kind of like the unique identifier that goes into this learning. And then you want to transform that into like a real vector space with n dimensions, and it's like something like 100 or 200. So, for example, the embedding of train or the ID for train would end up in this thing, and the ID for the embedding of track would end up in this thing, right? And so now we have these two vectors, and we can like do, for example, Euclidean distance. We can do cosine similarity, and so on, so we can compare how close they are to each other. Okay, so that's kind of like what we want to have happen. And then, so what you see here is a couple of examples. Here you have like, for example, the word of director, and then like around director you get like all these different kinds of like different types of words, and so that's like all kind of related to each other, right? And this is kind of only like a small snapshot of what's there. And then, but here you also kind of see like something else happening. So what is happening here is that you can start off with like these all, both, many, several, and so on. And then you can basically see that there's like some sort of like a gradient in here that changes from words to numbers, and so you can have these kind of trajectories in these embedding spaces as well, and they can be very, very interesting. And so these trajectories, we'll talk about that in a second, but these will be very useful to do, for example, also some surrogate testing. And then, similar to director here, you could, for example, look at a word like France, and then look what are the nearest neighbors, Jesus, what are the nearest neighbors, or Xbox, and so on, okay? And so you can find these kind of topic areas in this model. And so I also brought one of our examples that we have. So this is one of the embedding spaces that we trained in some context, and so you can already kind of, okay, so let's see what are these. So this is Wyoming, Portland, Georgia, Kentucky, Confederates, Vermont, and so on. So you see like, okay, there's like a location space. Then you have Butler, Nelson, Clark, Harris, Powell, Stanley, Eric, Jay, Kevin, Dick, and so on, right? So these are names, okay? And yeah, so these are mostly just names. Then in the middle here, what do we have? Alongside, seal, besides, background. I don't know, this may be a bit more fuzzy in here. Certainly, exercise, evidence, and so it's not always like very clear what the relationship between the words are. Feed, beating, diet, foods, meat, cheese, cream, drink, coffee, cotton, interesting, like another resource. Aged, age, year, schedule, month. So it's very interesting, like what kind of relationships you can learn in these things, right? Boxer, champion, champions, rugby, athletics, tennis, players, NBA, coach, and
So
so
is
on.
this one article that you fed through, or these are like series of articles, very diverse, obviously, from civil
If
war
I'm not
to-
100% wrong, I don't know.
Uh,
So if I'm not wrong, this is from a conversational data set. So this is about like
I remember
10,000 conversations of like
Of
10
over the
minutes.
phone, right,
Yeah,
yeah,
over
yeah.
the phone. And then, but you don't actually have to do this with just words. You can also do this with audio, right? And so here's something that we learned with audio, and this kind of relates back to what we talked about. And one of the things that we were kind of working on is to combine the audio and the words. And so like this green part down here, if you look at it, vocals sound garbage. No, you're not. Listen, sick and tired. I'm sick and tired of listening to you, damn sadistic bully. You're a beast. Hate. Stop it. Stop it. Stop it. Stop it. I hate you. I loathe you. And so like you can see like the green parts already. Like that's
Pure
anger,
anger.
right?
Yeah.
And then yellow is the sadness again. It's like I don't know, like but yeah, you can do this with like sounds. And here we looked at the sound representation of that word here, and this is the context in which it happened. Okay, and so yeah, so we're working on these kind of things. So you don't have to just use text; you can use audio as well. Okay, so. But this is just like the neighborhoods. But let's look at like what these gradients or these changes here could mean. For example, so there are also different properties in here which allow us to, for example, have like a vector or like a we can look at the distance or like the so each of those have like a vector location with respect to the origin, and we can basically subtract them from each other and get like this change vector, right? But we can also take this change vector and apply this change vector to other words. And what the interesting part is that we can learn for free actually these kind of changes in the vector space. So we have, for example, the word man, and we can walk along this change vector to woman. But then we can apply this change vector also to uncle and find aunt there. And we can apply this change vector from king and find queen there. So obviously this change vector, this direction of moving through that vector space, now represents something, right? It represents actually the change from a man to a woman. So that's kind of like a gender vector in there, right? And this is completely learned off of like this distributional hypothesis. What we would hope to do in our case, in my sort of research, we would want to be able to walk from man to man and from uncle to uncle, but then from like man to man, and basically have a change in emotion in there. And then we could like hopefully take the difference between man to man and take that vector and add the man to woman kind of average vector for all the other words that where you have the word woman or man present in your data set. And you can then find the differences between words and their affect relationships. So that's kind of like where we want to go. And so yeah, this kind of like learns this gender dimension, and this is really cool. And now, because these are vectors, you can really just like subtract and add them and do stuff like those, like that. And obviously, like it's like it might look a bit trivial in the sense that obviously, like if you walk from man to woman, you get this change vector. Like if you add this to uncle, you're not going to end up right exactly at where aunt is, right? Mm-hmm. But you would end up in like the neighborhood, so you would still have to kind of search for what's the nearest neighbors and so on. Okay, so that's like it's not like that you would exactly end up at that location. Okay. But for example, you could use this if you have if you don't have the word aunt in your data set, you could just end it up there, like put it there if you wanted to do so, because you can fill your space with missing data if you just use this and like kind of assume that it was learned. So that's kind of like another interesting avenue there. All right. So what other properties can we learn? Well, here man, woman, queen, and king again. But then, for example, walking, walked, and swimming, swam, and like relationships between countries and their capitals, and others like Sarkozy, Nicolas, and like and is Berlusconi, Silvio, and Putin, Medvedev, and Obama, Barack, and so on. So this kind of very interesting dimensions that you kind of just get for free if your data set is just large enough. Okay, so these are almost learned as side effects, and in fact, actually, because it's really hard to evaluate, like how good is this, right? Like I don't know, who can say? Like nobody can really tell how good this is. But one way to evaluate how good it is if you have like a subset of like, or if, like a set of analogies that you want to basically try to like check if you have them present. So this could be a good surrogate task to evaluate your embeddings. Okay, and yeah. So how do you learn this? Well, how does word-to-vec learning work? Well, what you want to do basically is you want to predict the word that comes next, or is in the middle, or before a certain context. So you can have, you can use the context of like what happens before, and we'll see how that looks like, to predict the next word. You can predict the center word with the context around it. You can predict the previous word with the context after it, and you can use the context to predict that word. So we will leverage the context around these words to predict where these words should be. And one trivial way to do this would be, for example, if you compute the softmax based off of your context that you have, you want to predict a word at a certain time or like a certain location within that. That becomes really, really difficult because guess what? You would have to compute this, the score for every single word in your vocabulary. That would be like 1,000,000 words, right? So this is how this would look like. So you would have the cat sits on the mat, and you want to predict mat, so that's the target word, and you want to actually have this to be a lot larger in the output than every single other word, right? And to compute for this for every single other word, like you have to run this a lot of times, and it becomes very, very complex to compute this, okay? So that's not what we want to do. So this would be kind of like in the ideal scenario. However, what we are actually doing is the following. We basically just predict what this word will be in contrast to a bunch of words. So you have like 5 or 10 different words that you randomly pick in your vocabulary, and you just want to make sure that your word is like the value that you get for the score value that you get for your word is a lot larger than the average or the expected value for a noise word. And obviously this noise word estimation here that you have to do kind of stands and falls with the size or the number of noise words you pick, right? You can for example, imagine if you just pick one noise word, well, that's not very accurate, but if you pick 100, well, now like you have an accurate estimation of like how the noise would look like, but actually that costs a lot of time again to do. So what you want to do is like find a sweet spot between like too little or too many of these words. Alright, so this is kind of like the idea. We're going to go into a bit more details of this on Monday, but I think we need to wrap up here for now and have you guys start with the presentations. And if there is a volunteer to do the first, if not, I will pick the first. And you know what happens with United.
Oh.
You can go first.
Okay. So, if we don't have volunteers, we'll volunteer.
Wow.
Yeah, my thugs are already waiting outside. So.
Okay. Okay, you're scared now. Yeah, I'm not able to play it from here because this one is stupid. There's no, I don't have the oh my god. Yeah, okay. Cool.
So I'm working on the cleft lip project. And it's in partnership with Operation Smile. As promised, I have pictures this time. So mostly just a lot of cases like this. I can't show the specific pictures for HIPAA reasons. A little bit more background info. So in terms of a project update, I finally got all of my images. And we don't have any of the cleft palate ones where like there's a hole in the top of the mouth. We just have like the cleft lip ones. So it makes my task slightly easier. Furthermore, most of the pictures are just like this, where the mouth is shut, so I don't have to even worry about them being like having cleft palate on the inside. So baby steps. So my objective changed slightly from the last time I presented. Essentially, they were only able to get me a limited data set, and it wasn't very different. But there is one thing that they were very interested in getting, which helps with their current papers, is they want to be able to quantify cleft lip from just looking at it. Now, the way they traditionally do it is they take these measurements of different dimensions of the cleft lip. But kids are really young and squirmy, especially at this age. They're very small. And they don't really like sitting in one place, much less sitting in one place and letting them measure their mouth. So they challenge me. They're like, if we give you a picture, can you give us a number? So, yeah, challenge accepted. Oops. Okay. So I think when I first met with Li Xing, he was like, you should use open face. I was like, yeah, sounds good. I was like, does it work if like part of the face is cut off? He was like, well, that's a good question. So I looked into it, and it seemed to work really well for recognizing a face and cropping it, but then I wasn't too sure about the feature detection aspect, especially like just the lips and like a high quality trace of the lips. We also had another problem. Once I got the images, I realized that you can't always see the eyes because they sometimes have taped over the eyes with like surgical tape. And I think I was kind of messing around with Snapchat because I was like, okay, if I tape over, like Snapchat also uses like feature recognition, because like, you know, you can have like purple lips if you put on the right filter. So I was like, I wonder if it works on Snapchat. And then, so I like literally taped over one of my eyes just to see if it worked. My friends got a really good kick out of it. And it was still able to trace my eye. So I was like, wait, let's just see what Snapchat was working on.
Alright.
So I was on YouTube messing around looking for just, I'm not sure. Oh, I guess, yeah, there's no sound.
Oh, the volume is coming up there. Oops. Oh, you got the wrong one. That's good.
Between light and dark parts of the image. A pioneering facial detection tool is called the Viola-Jones algorithm. It works by repeatedly scanning through the image data, calculating the difference between the grayscale pixel values underneath the white boxes and the black boxes. For instance, the bridge of the nose is usually lighter than the surrounding area on both sides. The eye sockets are darker than the forehead, and the middle of the forehead is lighter than the sides of it. These are crude tests for facial features, but if they find enough matches in one area of the image, it concludes that there's a face there. This kind of algorithm won't find your face if you're really tilted or facing sideways, but they're really accurate for frontal faces, and it's how digital cameras have been putting boxes around faces for years. But in order to apply this virtual lipstick, the app needs to do more than just detect my face. It has to locate my facial features. According to the patents, it does this with an active shape model, a statistical model of a face shape that's been trained by people manually marking the borders of facial features on hundreds, sometimes thousands of sample images. The algorithm takes an average face from that trained data and aligns it with the image from your phone's camera, scaling it and rotating it according to where it already knows your face is located. But it's not a perfect fit, so the model analyzes the pixel data around each of the points, looking for edges defined by brightness and darkness. From the training images, the model has a template for what the bottom of your lip should look like, for example. So it looks for that pattern in your image and adjusts the point to match it. Because some of these individual guesses might be wrong, the model can correct and smooth them by taking into account the locations of all the other points. Once it locates your facial features, those points are used as coordinates to create a mesh. That's a 3D mask that can move, rotate, and scale along with your face as the video data comes in for every frame. And once they've got that, they can do a lot with it. They can deform the mask to change your face shape, change your eye color, add accessories, and set animations to trigger when you open your mouth or move your eyebrows. And like the iOS app Face Swap Live, Snapchat can switch your face with a friend, although that involves a bunch more data. The main components of this technology are not new. What's new is...
Okay, so I think I thought the video did a pretty good job of explaining the algorithm, so mostly just decided to show that. So that is the goal. And so essentially this is an overview of my experiment. They finally just got me the numbers yesterday, so a little bit behind, but playing the catch-up model. But yes, I'm also planning on using the active shape models to find the lips and then create the measurements. And then the goal is at the end to just run a regression, but I'm also trying to figure out what else I can do, what other models I can try to compare that to see if it's a more accurate fit. So I have already run into some limitations in addition to like the surgical tape and then a few images that weren't very ideal. Again, there's only 70, so I'm using the leave one out testing and then using a few different models to determine the best fit. So yeah, experiment data to be announced as soon as I consolidate all this.
Great.
Okay.
Other questions? So basically a comment also, like, so OpenFace uses the active appearance model as well.
Oh, it does, okay.
Yeah, and there must be a way to, like, have it only search for lips.
I think, yeah, if anyone has any ideas, that would be
Yeah.
appreciated.
Because all the points are numbered in OpenFace, so you
Yeah.
know that I think 51, we had it,
64, yeah.
64 it's a quarter of a nose, right?
Yeah, if
and then something like
Okay.
that. So you will be,
So just select for a certain number of
Yeah,
points.
just
Yeah,
Google
when
the
you
action units and you'll get all the points for the.
Okay.
Yeah.
That's good to know, I didn't know that.
Okay.
Yeah, and then
Okay.
the other option obviously kind of would be to basically discuss all like the issues that you have with doing what you, or like trying to do what you're doing, and then basically assuming that you have at some point like an active appearance model for the lips that would work, but until then you could try to manually annotate yours
Okay,
yourself.
there's only 70, so it should be.
Yeah, so it
small,
shouldn't be too much.
Okay,
So that would be another option,
okay.
right?
this for sure will work, because we were measuring distance between the top of the lip and the bottom of the lip
Uh-huh.
in our last semester, so we know what these points are, and you will know what these points are.
Okay,
You might not know that there is a cleft lip,
okay.
because that will not be
Right.
in
That
it.
is different, okay.
Yeah, but it was, so I would say, discuss all the problems that you have, try with open face to locate the face, and then
Okay.
try what Natasha was suggesting, to use
Okay.
those locations, but then compare that performance with like your manual annotations, like how
Okay.
well it could be,
And just figure out how well it correlates.
right,
Okay,
so that would be.
Is it video or still?
it's just pictures.
Okay,
Yeah,
that's
it makes
easier.
it so
That's
much easier.
Because we
Yeah.
were doing it on video, on,
Uh-huh.
I think 60, 70 videos, and we were measuring during that, quite a bit, like a couple of minutes, how the lips move.
Okay, and it worked well.
It worked well.
Okay, that's much appreciated. Okay, thank you.
Awesome, thanks.
Maybe something.
Do you guys want to go first?
Oh, go.
Sorry.
So on open source, when you get the whole file
Uh-huh.
they sent you, so look at
Yeah.
the, if you look at the whole file, the first, yeah,
Let's try to be in time.
first, let's see, there's actually since a new already
It's on the
interpreter.
Oh,
The
okay.
first series is very broad and,
companies?
You guys just tell me when to forward, or do you wanna, otherwise I can't take notes.
Okay, we'll just let you know.
Okay.
Hi everyone, my name is Asko.
And Cindy?
Yes, we're the team who worked on the predicting IMDb scores with a bunch of features provided by one of the IMDb, the database.
So for this project, we hypothesized that there's a strong correlation between movie information, like the budget or the director name, and the IMDb score that it gets. And so we can apply machine learning regression models to predict the score before the movie's released.
Yes, and here we
So for the experimental setup, we first put missing values at 0 for features like the director's Facebook likes. And then we removed features that are only known after the movie has been released, like the gross or the number of critics it got. And then we also did some string conversions to numerical values for the word features. So for features like the director name or the actor name, we mapped the unique names to unique numbers and then substituted those numbers for those features. And then for genre, we separated each genre type into different features and just did a binary 0, 1 if it followed in that category.
correct. For here we actually that was actually the main thing we did for the data, because there were quite a lot of data was in the format of string, so we did similar thing as word to vector conversion. For the genre, what we did, for example, one movie can be clarified as fiction, action at the same time. So we actually expand those features, and we give use a binary way to identify it. For example, there's one feature called action, and if this movie falls into that category, we give a value of 1. If it does not, give a value of 0. So we actually have like almost like 50 genres. So we just do that we add another 50 column on top of the region data, and give it all binary and performance on top of that. And another thing we did was actually with the plot keywords. For example, on the words aliens happen in Avatar and in another different kind of movies. So with we kind of want to correlate the plot keywords with the IMDb score. So we find all the movies that have alien plot keywords appear with them, and average the IMDb scores on top of that. And we use that IMDb score to represent the aliens keywords that happens in plot keywords. And for each movie, we pick the top 5 plot keywords and use the summation of the average IMDb score as a numerical value for that specific feature. So that was what we did for the string conversion. And another thing we did is also like just regular synthesis for the better performance, more stable. We did split it into the training set and the test set, which is like 20% compared with 80%.
And then, so for the experiments we ran, we did 3 different models, support vector regression, multiple linear regression, and then a random forest. And then we used scikit-learn and bridge search with fourfold validation to tune the parameters.
Yes, and here is by like for the evaluation of the performance of the training model, we evaluate the method using mean square error, the mean absolute error, and explain variance and R square. So the result we got here was actually we realized actually the random forest regression actually performed the best out of all the everything. And what surprised us a little bit in the beginning was support vector machine linear regression actually performs a little bit worse than the multilinear regression. And then we look into the code, we realized for now the algorithm we're implementing right now is the support vector machine. The scikit-learn, we only use the default one, which is RBF, the method to train the model. But we're interested in applying, probably try to explore the linear method, which takes a long.
Yeah, so one of the reasons why we couldn't really play with the support vector linear regression other kernels is because when we ran it with like linear kernel, it took forever, like it hasn't stopped. So we just stuck with like the default RBF kernel.
So we're still trying to learn that. And on top of that, overall, like in the original blog post when they put the data set, they achieved like performance of for mean square error. They achieved with random forest with 0.89. So here we got the value with 0.8. So based on like by doing a bunch of string conversion with actor name, country, and plot keywords, I think we beat them by almost by 0.1.
So the person on Kaggle like took out all the string features and just did numerical values.
Yes.
It's interesting. Oh, cool.
And then for our next steps, we're going to try a neural network model and then do other word conversion techniques. And then we're going to try and incorporate more recent movie information.
Sounds really interesting, Guardians of the Galaxy. I like that one. Guardians of the Galaxy. I am Guardians of the Galaxy.
Any questions?
Cute, very cute.
So yeah, I would. It would be interesting to understand like what what features seem to be working best. So for example, you could try some other feature selection methods like forward selection or backward selection. You start with every feature and then you remove features that are not that helpful. But also you could try and see like let's say the subset of the genre features helps this much, like so train it with and without those and compare that. And a couple other things. I think it would be interesting to just maybe add like a statistical analysis here. Like you don't, for example, you don't need all of these numbers here. Like after the 3 numbers, you can just leave that out. That's something for everybody. Like we don't need this much precision, so you can just like leave this part out there. And then you could add like the variance or the the standard deviation of each one, like for because this is the mean, right, over the 4 folds. But you could actually also add the variance of standard deviation so that we can see, for example, random forest. My guess would be that it could have like quite a bit of a variance in there, but I don't know for sure. So that would be something to look into and to investigate and see what's happening there. So that's just another suggestion, and maybe you can like do some correlation analysis as well with your new features with the IMDb score. So maybe there is something like some features are better than others. It would be interesting to just know. Okay.
So was that forward? What the features that?
Feature like sequential forward feature selection, and scikit-learn has that in there. You just say just look up feature selection first.
Also, good question for support vector machine, because like different kernel ROM, so runtime is quite significant.
Yeah.
Like how do you have any?
So with the linear kernel, I guess it might be too many features, and
should we do PCA on top of that and then try to optimize?
yeah, or you do like feature selection again.
Okay. Try to test with a few features instead.
Yeah.
Okay. Thanks.
Okay.
There's I think this is
Next.
wiki on
So, what is the p-value
so
in
it's a-
statistics? What is that?
P-value basically gives you the probability of like having a difference in the observed distributions of samples or
Okay.
no.
Will you ask that for that too? Are you looking for that as well?
Yeah,
Okay.
that would be good.
I know we did something last night and we, actually they were talking about that.
You have the distances, you can measure the distances, so you will know how big is this, or how big is this.
Yeah.
No, but this is something that will speed it up, right? This is,
I hear it, but I can't hear it.
Hi everyone. What I'm doing is the custom flow forecast on this is a website which is actually pretty like Yelp, which is a branch of Alibaba. They hold a challenge by on a conference which is IGCAI 2017. So I use that data set to do the customer flow. I have introduced my data in the last report, but I still want to have a brief introduction of that. It was basically a data set of all the payment records in the 64 weeks, and we used this to predict the flow of the coming 2 weeks, and this is the how we evaluate our outcome. And basically, this is just a arrow between the prediction and the ground truth by each shop each day, and the average of it on average. This is the data description, not that very important. Just which is the shop information is provided, and the view and the payment information is provided. And this is important. This is our data set, and which is provided between. This is the test data. I filter the test data from them and keep them away from the training data. This is, so last time I said I was trying the random forest, but then I find a new model to very suitable for this situation, which is the ARIMA, which is short for autoregression integrated moving average, and which is the combination of three parts. In the autoregression is kind of like the regression, and for the moving average, I think if I understand it correctly, it is the like if you go up to like reach a point, you will flip your prediction and get like oscillating curve, and it is very suitable for the like economic growth prediction, and because in our data set the shops the data of shops indicate a pattern in their data, because in the weekend the customer flow will be higher in the weekday than weekdays. So this kind of pattern. This is just an example. We will see later how it performs. Basically, my idea is to train this ARIMA model on each shop, and because each shop has different patterns to predict, and apply the best parameters to each shop, and here I use the grid search for the best shop for the best parameters, and this is just a random shop data, and for this blue data, this is the data in the test set, and the green curve is what I predict. Basically, there are shops that fits better than this one. This is just a random shop, and looks like it fits pretty good. And
you're starting your prediction at 1, right? In the beginning it's perfect, and then you.
Yeah, this is behind it. Before this is the training.
Yeah.
The training. This is test data and my prediction. But when I run the event evaluation, this is not so good. The error is 0.26. I think the problem is that for some of the data set is pretty weird, because in ARIMA for example I use the data set like if behind this point is our test set, we need to make our prediction. I just use this period of data to train all the data before the zeros will be get rid of. I will get rid of this data, neglect that data. So basically, in the circumstance that in the training data end with 0, the ARIMA will output just the average of all the data before. So if here is the end of the training set, and I will never predict the customer flow like this. I think the problem is that I just use the history of the shop and neglect the other features like its similarity with other shops like them. Like they are all ice cream shop, and other ice cream shop have the the same curve like this ice cream shop, but I will get a wrong number. But for some suitable case, in some case, the ARIMA works pretty well. So I think what I need to do is do a model ensemble. Basically, I think I plan to run like a cluster algorithm like KNN to find out which shop will be suitable for ARIMA model, and for the random forest model the random forest model works on the average better than the ARIMA. So I will use the random forest on the other data set. So in the last report, I used these features to do the random forest and do a fairly good outcome, and which is the sum and the average in the sliding window. Oh, sliding window. I used the sliding window idea of sliding window to do the training. I used 4 weeks of the time slides to use as a window and predict the coming 2 weeks of the flows, and I train on this one. Oh, this is like this. Like I train on this one and predict this one and validate and train this one and validate this one. It's like a sliding window. Previously I got the 0.16 around 0.16 error, and now I add more features of them. First I add the official holidays into the features, and other special days like the November 11th, which is pretty like the Black Friday in America, and the shop categories like ice cream shops and other ice cream shops. And I also find the hot pot shop is pretty different because they are just weirdly shut out in all the data set before the ending of the training set. So I think I need to train them separately, and I also add the weather condition, because the weather condition definitely will have an influence on our outcome. So right now, previously I get around 0.16 error, and right now this is 0.08, and I think this is a pretty good outcome. And so in the then in the next, I think I need to run LSTM, and I already built a small demo on the Keras, pretty small. It is currently have the arrow at the 0.15, and then I think I want to use the K-nearest neighbor to find out the shops that are suitable for ARIMA. And yeah, my friends tell me that GBDT is a very famous model. I think I need to try this one. But I think GBDT will perform not better than the rainforest, I guess, because they are kind of similar. Thank you.
Okay. Awesome. Questions? Yeah, I think I like the idea of trying to find like clusters in the data and try to maybe learn the agreement like from multiple together. And yeah, so I wouldn't try too many models. Like I think you stick to the random forest agreement, the LSTM. I think you're fine with it. Okay. The GPT. Cool. Thanks.
Yes. You wanna say anything? We're going to use your computer, right, because mine is. So we're pretty types. They can come in. Not a pretty sight, so we're.
Oh, yeah.
Yep. Steve.
Yeah.
Okay, so what we're trying to do is a bit, it's a bit hard for evaluation because on generative models, evaluating how successful you are is fuzzy. But generative models are quite interesting in art and architecture, and I found a couple of examples of research that is trying to create better tools for art or sometimes even architecture. So this is Magenta, Google project Magenta, that is creating duets with the performer by using machine learning, and we will show you a little bit. So you play a little bit and the algorithm generates the chorus or whatever is the orchestra for it. So the goal is probably not to replace completely it's not to replace the composer, but give him more tools. I saw a couple of talks by the guy who is running Magenta, and what he's saying is when electric guitar was first designed, first thing what guitar players did was really break the idea. The idea with the electric guitar is to remove distortion and amplify the sound. And as soon as people started really playing with it, they, of course, immediately broke it. And in art, usually you invert and convert the rules. Like Deep Dream is overfitted training set that you apply to. So his goal is to create tools that will work with the designer or composer in synchronous, so that you don't have to break it to create art. And I would say that there's an implication for architecture, because there's a whole part of architecture that is basically geometrical. And you can use the rules of geometry, and then you apply other stuff. So there's a space there. How fast? There's no money in architecture, so nobody will invest, but okay, it's kind of fun.
Okay.
Okay, so that's the explanation of the, I guess, motives, right? So what we did is we figured out that we want to have a data set and run different models. Pixel CNN is famous for working really well with images, and it focuses on the detail and understands the neighborhood of the images. But I saw these models are pixel RNN models that use two LSTM networks and are able to capture sort of a higher distance data. So we are hoping that from that we can learn that, you know, bathroom doesn't go inside of the living room. But in terms of geometry, we'll easily go there. I mean, it's doable, it's a valid move for Pixel CNN. So we will see. And then we want to contrast this with autoencoders and basically see what works the best without necessarily coming up with the brand new algorithms for this task, but just use what is available on the market. Downgrade it to grayscale images so we can have them slightly larger, and see if something like that would really learn the constraints and be a useful tool in a way of working with the designer on the other side. We'll see. So let's go to the next slide. So what we have is a data set, and one of the really cool features is that, again, it's insanely imbalanced. 75% of all the pixels are white. And then this was, and then I was really kind of considering in terms of what is white. White is 250 and 250, between 250 and 255. So these are really the whitest of whites, and it's still 75%. So anything else that will not take relationship into mind will probably, with a great prediction, just put in white images and be 75% right, which is because we worked with these unbalanced sets last time. Apparently we have that. But this is really different. This is why we need to use neural networks.
That's why we actually decided to go with the patch, filling the patch. Because for autoencoders, we are doing the patch filling. So for our autoencoders, like usually there's a bottleneck. Like in the last lecture, we had that. But because we are not regenerating the whole input, we are just regenerating a part of it. So we need the other part of the picture as it is. So we are using a fully connected autoencoder. And
so this was the story of a data set. We scraped 10,000 images, we pre-processed them, cleaned them up, you did filtering, sharpening, and one of the bigger problems is if we would resize them to fit, we would use the actual qualities that are making it a floor plan. So we had to crop and resize and pad. And we decided to pad on left and bottom side instead of centering it and cropping it to three pixels all around. So anyways, there's some things that we might actually change it if that ends up being a case.
And for the data set, we need different kind of images for pixel CNN and different for the autoencoder. So we're still figuring out how do we resize them, because this resizing is really small for the autoencoders. So that's why we just resize like 64 manually so that we can feed them into the autoencoder and get some results temporarily. But yeah, that's why the pictures are really fuzzy and they're not very...
We scaled them up just to show you how things that are learned so far. So you learned that the background should be white. You learned that walls has to be extended. So I think next images are better examples. So walls have to be extended, and it extends walls. It kind of gets the idea that walls are extended.
Even though it does not understand where does it stop and things like that, but yeah, it's extending.
It is extending, and then there's few more. So it also learns that text, which is basically this. If it shows up, it needs to be extended into smudge. And this is our best result, where it kind of worked really well. There's a bit of a gap, but look at this, there's a text that you kind of realize that it needs to fill it in with something. So ends up being interesting. We don't have only residential data, we have a whole lot of different data, so it's going to be very interesting to see what pixel CNN will do. And we want to see the difference RNN and CNN, if there's more meaningful stuff that can be kind of retained in these long connections that CNN might lose.
Okay. So what's the schedule for the data set that you think you're gonna...
The data set is cleaned. So we need to start running it. I'm currently trying Pixel CNN on MNest, and it's been running for 2 days. So I probably have to kill it now and make a smaller set and just run CNN.
And
And we'll try to make auto encoders better, and after that we'll try pixel art.
so for me to better understand, like what the autoencoder gets is basically, so you said it's a fully connected autoencoder. So you have the image goes in with the white patch as input, or?
Yeah, with the
Okay.
white patch as the input. So it's just the middle patch that we've removed. First we've trained the autoencoders with all these images. So it's just like we put around 64 images only, like these 64 only, and we are making it regenerate the
white
patch.
patch.
Yeah.
So you give it in training it sees the entire image.
Yeah, it sees the entire image.
And in testing it sees the image with a white patch.
So it tries to, yeah.
Reconstruct the
Like the paper we were reading on, what it does is they send the patch that they've removed to, and with the loss, like it generates something, and in the discriminator it tries to get the loss between the patch it generated and the patch that was actually there, and tries to better it.
Wait, is it using an autoencoder or generative adversarial network?
No, that is GAN.
Oh.
That has a discriminator
This is
also.
GAN?
No, this one is just autoencoder.
Okay.
We don't have a discriminator for this one.
Okay.
The paper we were reading from had that, but
Ah.
yeah, we didn't do the loss function yet.
You gonna do that, or?
We are still trying to figure
Okay.
out. Maybe
Yeah, I think
add
the
that.
3 months is fine, is enough. I'm not sure if you wanna.
We've not started working on the pixel RNN, but yeah.
We will.
We will.
I mean, yeah, like balance it out, like see if it's better if you run it all on like just 2 months instead of like adding another one. Yeah. And how do you plan to evaluate it?
Yeah, that's gonna be.
So it's gonna be somebody that, it needs to be somebody from a profession just making sense. Does it make sense or it doesn't make sense? Because it's specific knowledge. I would not even think about mechanical tips, so it's gonna be my students, unfortunately.
Okay. So they will like rate it in some way,
Yeah.
like human
Yeah.
ratings, okay. Great. Thanks.
It's gonna be frankly, it's silly. She pulled the biggest part. It's me and she said to. I prepared everything for MATLAB because I like MATLAB, and yeah, she loves MATLAB. So you can put visual disability. Sorry,
This is my project, and it's like the main purpose will be like predicting the setting of the default payment, and some purpose will be like try to predict the user's payment behavior, such as like whether they are going to pay their bills on time or they are going to be late, and the motivation is like first one is like well analyzing the user behavior, their payment, and it's good for social study. And I think the second one will be the most practical. It's good for the bank manager to have some overview for their new users. And yeah, this is the data set, and I'll just skip it. And this is the one of the example. And while I was analyzing the data, there was a limitations, like for some data they don't have the bill amount and the payment amount because they don't have any activations or activity payment during the time. So at first I was decided whether I'm going to remove it, but after that is like this actually for from a bank manager aspect, it doesn't matter, and it is good for them because they just put their money inside and do nothing. So after that, I just decided to keep the data. And like, the algorithm I'm going to use, and most of them will be the clustering and decision tree and using SVM. And this is the first experiment, and it's like this is the data, and for the male in the gender for male and female is almost 1 to 2, and so yeah, pretty interesting. It's like almost like 1 to 2, and but after for the analysis for the payment default payment method, it looks like almost the same. So in the first experiment, I just decided to separate the training and validation and testing data randomly because it looks like almost the same. So yeah. And in the second one, I decided to separate their user age into groups. For the first one, it's like 21st to 24th, and it represents the student, kind of like master student, or they are still students. And for the others, like here's like the 3 range, and it represents the users who are now working. And here like the 2 groups will be like some people like they are already married or they have a stable lifestyle. So I just cut into this. And for the rest of it,
highly exaggerated.
yeah, and for the rest of it is like for the people that was retired, and also, and I think it would be good to cut them together because like we can see from that image, for the user over 61 years old, they have fewer data, so I just put it into a group. And for this third experiment, I decided to separate the training and validation and testing data into like 3-fold, and it's like equally. And just like for in the male and female, and we can see there's like a slight difference around like the first one will be like here, around 22 and 23 years old. Will be like here, and another one will be like 32 to 36. So I just try to separate them into equally.
Mm-hmm.
Yeah. And the next step is like I'm going to try to set out another experiment to combine the marriage and with the age, or the education with the age, or the marriage with the education, and set up another experiment for these attributes. And this is will be the evaluation. First, like the error amount, and I think most important will be the accuracy rate. For setting the default payment, and if possible, it's like for the sub goal, I will try to get the possibility to predict for the new user based on their gender, age, education, and marriage status, and also for their studying amount, and try to predict for like 6 months, the first 6 months, whether they are going to pay their bill on time or late. That's all.
Question. Because like if you visualize these distributions, you should make sure that like you have the same scale on both plots. For example, here like the scale goes from 0 to 140, and the other one is like from 0 to 250. So that would be nice to see, and then also like you might want to think about like visualizing that a little bit differently as well, with like a box plot or something. But yeah, so for the evaluation, are you gonna look at like payment amounts, so that as a like a continuous number, as well as like late or paid early or paid on time? So are you gonna do classification and like more of like a regression like evaluation?
The first priority will be like predicting they are going to reset their default payment or not, and
Okay.
the sub goal will be like predicting the payment status.
What kind of classifiers are you planning to use?
First, I think most of them will be like using clustering. Yeah, just like putting them into groups and then like using decision tree and run for a classifier and like gender and age and education or marriage and try and to go through it and we'll might use the SVM and for the possibility we'll use the INF base.
Okay. Thanks.
Yeah, so my project is I'm doing affect recognition systems using recurrent neural network combined with convolutional neural network. The motivation behind the project is that like emotions are important in human communication. So we assume that if we implement the ability to perceive people's emotions into the machines, it can like improve the efficiency of human-computer interaction. So the data that I use videos that contain facial expressions that labeled with 6 prototypical emotions from MMI database. So they are like anger, sad, sadness, disgust, happiness, surprise, and fear, I think. Yeah. The data in the videos, the facial expressions are like post-facial expressions, so it's not like naturalistic and spontaneous facial expression. So first, before I train the model, I had to convert the video into image sequences, and I downsampled the video from like 24 and 25 hertz to like half of it because to reduce like the complexity of the training step. And also like before I feed it to the model, I turn the images from like change the color system from RGB to grayscale and downside the images as well.
This is my appendix.
Yeah.
Yeah.
Okay, for my experiment, I will compare between like 4 different approaches. The first one is like just in the meanwhile, I want to use the SVM with LBP top features as a baseline, but in the meanwhile that I'm studying how to use them, I also try to use LSTM with like no space reduction on the data. So basically I feed the entire images into the LSTM and see if it explains anything at all. Because if it works, I wouldn't have to bother like using any feature extractions, right? And then I also try to use the LSTM with LVP features compared to like if the one that I combined with the convolutional neural network can like work better. Yeah. So for the LVP feature is like, LVP is like a texture descriptor that describes each pixel on the image by like calculating so yeah, so each pixel it will have the value and it will use that value as like a threshold to combine like the binary digits for like the neighborhood pixels. And for the coordinate that is not like integer, it will do like interpolation to estimate the value for that pixel. Yeah. Calculate the binary value and construct the histogram after that. But in the application, it will use the uniform patterns to reduce the possible combinations of the binary values to like 16 instead of like 256. So this is like the first that I'm gonna try. So basically I feed the entire images into the LSTM and predict the result. This is the system that I will use the LSTM with LBP features. So I use LBP to extract, I feed image to the LBP module and extract the LBP features and construct the histograms of each image and feed those histograms to the LSTM. And this is for the baseline model. So basically, the LBP top is like the three-dimensional version of the LBP feature. So it also takes into account the temporal axis of image sequences. So for each image sequence, it will construct a single histogram and feed into like the SVM to predict the result. And the last one is my proposed approach. Is like I'm gonna train the CNN with like separately, like pre-train it first with images that I sample out from my data set from all the sessions. Yeah, and then I will add it to the system and then feed image sequences into like CNN and extract the feature. And feed into the LSTM. And this is just some preliminary results. Like, so I tried the first approach that I feed the entire images into the LSTM, and as we can see, like in the early stage, the behavior is pretty random, and after that, it kind of got more stable, but it doesn't seem to like learn anything at all because the error rate is around like 0.80 to 83 around that. And for the orange line is the error on the validation set, and the blue line is the error on the training set.
There's something going on there.
Yeah. And this is the system that I used LSTM with LBP features. I trained, I ran around 500 epochs, and at first it seems to learn something, like the error rate gradually decreases, but then it just overfits around like at the 100 epochs after that, because the error rate for the training data is just like keeps going down, but for the validation data it just goes up. Yeah, so for the level 1, I use the LSTM with 128 hidden layer size, and it overfitted, so I try like downsize the hidden layer to 64. It gets a little more consistent, but it's still overfitted. I think it's because like the feature space is pretty low, like 16 values compared to like all the hidden layer size, which is 64 is pretty big. So I might try doing the hidden layer size and see the result after that. Yeah. So what I'm gonna do next is like I'm gonna start training the baseline model, and also like doing the hyperparameters for the LSTM that use LBP features, and then start training my convolutional network and train my proposed model. Also, we will use accuracy and F1 scores to evaluate the models. But also, I might use the confusion matrix to see if like the model confuses between like which emotions, which one. Yeah, and after that, I also might try using my model to predict emotions from the videos from like other sources, not from the MMI database, to see like if it generalizes well.
Cool. Yeah, I think So are you just extracting LVP features from the whole image?
Yeah.
You might want to focus on the face. Try to like locate the face first. Use OpenFace for that, for example. And then also you are kind of causing like creating a little bit of a problem for the LSTM maybe by reducing the sample rate by half. So that might make it unnatural in a sense, or like you lose a lot of information from the transitions. So you might want to think about that and try to but and double check with your training. There's something going on that's not quite correct, I think. Like the first one, definitely I would throw that out. Don't bother about the image in and prediction out. Yeah, I wouldn't try that. Okay.
Can I ask, sorry, maybe it's stupid, but OpenFace will give you this vector map of a face that might be better feed for your LSTM than, it's actually quite interesting.
Okay.
I don't know if it exports every single one, or just the last one or something, but
No,
there's
it's
a
every single frame.
every single frame will have that. So you will have it, and it's basically just movement flow vectors that will, if you have sequences, it might actually be.
Okay.
Yeah.
Yeah,
I think
makes sense.
that would be better.
So you filter it, forget about the image.
detect if I turn left or right?
Yeah,
It will.
It detects your like.
Like you get like 400 plus features,
Yeah.
and
Yeah.
you do feature selection on it, and
Yeah.
then the best features are.
But this will really send you just images, because you don't care about, it will literally just take the face images, and you will not reconstruct the face and give you the flow. You don't care about the color schemes
Yeah,
that
yeah.
the other one captures.
Yeah.
So it might be interesting.
Yeah, that's right. Thank you.
Okay.
Might
I
have
love
to
this.
move you to next week.
Because the other guys are waiting
Yeah, I think
outside.
there's another class coming in. Is that okay, or?
Yeah.
Yeah. I can give you feedback on the.
You know, today's Wednesday, they don't have any.
report.
Okay, so on Monday?
Yeah.
But you have similar here
Yeah,
Yeah.
I switched my project
to something similar. Yeah, we should definitely see.
Right, thanks everybody.
So what are you using?
You guys aren't using the DC cam?
This again? Well, I don't think we're going to be using that.
Okay, yeah.
You're using this,
I'm like
this again.
following one of the papers that use
Uh-huh.
CPM, and then I'm trying to,
Like lab one, because I think we.
it's this one.
I'm not really at the.
Oh, I've seen it. It's bedrooms, right?
No, it's
No, no,
just,
it's
it's just
a-
face matching.
Oh, yeah.
Uh-huh.
So I haven't gotten many results because I need patient numbers.
Uh-huh.
It should work.
Yeah, yeah.
I'm using it like two different ways. One to like regenerate the original image, and then to like also conform to like it's like it's basically the same. It's basically the same.
Well, it's gonna be fun. Let's see.
Almost like
Cool.
published stuff, but they're like, I'm only gonna give you exactly what you need. It's like, okay. I'm like, yes, I need this.
No problem, okay, it's all good. Steve, we're gonna catch you next week. Okay. See you guys have a good weekend.
See you next week.
Yeah,
Bye.
all right, no problem.